Hello, we are team number 5 and our STEM project is as a water neutralizer. The characteristic of the problem is that in many homes a lot of water is wasted through the soap water from washing clothes, dishes, and cleaning. This water is called gray water and it's pretty difficult to reuse it because it is full of soap, foam, and dirt. Because of this, water isn't treated or recycled. A lot of families end up to use more clean drinking water. This increases the consumption of water and pollution, especially when the gray water flows into rivers or drains without a special treatment. Some characteristics are the unnecessary use of water, lack of domestic treatment systems, and low public awareness. The causes and consequences are that the problem arises because in many households, gray water from washing machines is discharged without any type of treatment, which leads to both water waste and environmental pollution. This water contains detergent, soaps, fibers, and suspended particles that involves turbidity and alter the pH. When released directly into rains or rivers, it can completely contaminate the water scarcity. The situation is made worse by the lack of domestic system for water treatment and by the limited awareness among families sustainable water practice.
SDG 6, Clean Water and Sanitation, ensures that everyone has access to safe drinking water and proper sanitation. It focuses on improving water quality, treating wastewater, and promoting sustainable water use. SDG 3, Good Health and Well-being. Clean water prevents diseases such as diarrhea, cholera, and infections, especially in children. SDG 6 directly supports better health and saves lives. SDG 14, Life Below Water. When wastewater is treated instead of being released into rivers and oceans, it reduces pollution that harms fish, coral reefs, and marine ecosystems. Proposal or solution alternative. Reusing gray water from washing machines is a practical and accessible way to reduce water waste at home. With a simple two-tank system, one to collect used water and another to treat it, becomes possible to safely reuse this water for non-potable tasks, such as watering plants, washing cars, or cleaning outdoor areas. It reduces both potable water consumption and household costs. In the context of droughts and climate change, this proposal offers a sustainable alternative that supports SDG 6 by promoting responsible water use and showing that simple, effective solutions can be applied at the household level. Justification. This initiative arises from the growing challenge of water scarcity, intensified by pollution, population growth, and climate change. In Mexico and many other countries, most households lack accessible methods to treat and reuse gray water safely, which leads to unnecessary waste of potable water. Our proposal provides an easy-to-build and maintain system that helps families lower water bills and reduce their ecological impact. It also promotes environmental awareness and responsible habits that contribute to long-term sustainability.
Beyond the technical benefits, this project seeks to achieve public perception. Instead of focusing on the cost of chemical treatments, we want families to recognize the long-term value of saving water. Water is life, and protecting it should be a priority. By promoting sustainable habits and encouraging environmental responsibility, this project contributes to a culture of conservation, starting right at home. Our 4 main objectives of our STEM project, water neutralizer, are: first, reduce water consumption by over 50%. Then, contribute to the SDG 6 clean water and sanitization. Be a low-cost domestic system. And finally, disinfect the gray water from washing machines. substance involucrated in the problematic and substance involucrated in the solution. Well, in the problematic, we have first the detergents, the soaps, the surfactants, the softeners, the oils, and the organic matter. Then, the substance involucrated in the solution are iron salts, activated carbon, and sodium hypochlorite. Description and characteristics. Well, in this part is basically the different part of our prototype and also some material that we use. First, we have the solid trap, then the two different tanks that the first one is going to be for the sedimentation and the other going to be for the storage. Then the pump, the filtration, the filter column, the disinfection unit, and finally the PVC pipes and the glue. Also, there are the measure of every part, and we add some notes about the sedimentation tank, the disinfection unit, and the coagulant that is going to aggregate fine particles.
The prototype is designed to treat wastewater from washing machines, purifying it for safe reuse and reducing drinking water consumption. The process begins with a solid trap that removes large debris such as buttons, lint, and hair. Then the water flows to a sedimentation tank where the pH is measured and adjusts to between 6 and 7. At this stage, a coagulant is added to help clump the finer particles together. While the tank is backwashed and the water is recirculated for approximately 40 minutes according to the product instructions, the system is shut down for 12 hours to allow the coagulant to settle to the bottom and remove the precipitate. Once the step is completed, a high-pressure diaphragm water pump circulates the water to a filtration system, where it passes through an activated carbon filter, which helps to remove odors and some chemical impurities. The clean water is disinfected with chlorine tablets to ensure the elimination of pathogens. At the end of the filtration and disinfection process, the cleaning valve is closed and the recycled water valve is opened, sending the clarified water to a sealed storage tank. At this point, the water is ready for reuse in activities such as irrigation or toilet flushing. Overall, the system's intent function is the efficient and safe reuse of washing machine water, demonstrating its ability to improve water quality, reducing environmental impact, and promote sustainable water practices.
Viability of solution alternative. The proposed solution is viable because it directly aligns with the project's objectives, reducing household water consumption by more than 50%, disinfecting greywater safely, and providing a low-cost treatment system that can be used in any home. Each stage of prototype solids removal, pH adjustments, coagulation, sedimentation, activate carbon filtration, and chlorine disinfection has proven effectiveness in reducing turbidity, neutralizing chemical residues, and eliminating pathogens. This system capacity to recover over half of the water used in washing cycle demonstrates its practical impact. Instead of discarding 70% to 120 liters per wash, families can reuse this water for cleaning, irrigation, or toilet flushing. Because the materials are inexpensive and require minimal maintenance, the prototype remains accessible even for households with limited budgets. Overall, the combination of low-cost, measurable water savings and reliable treatment performance confirms that this solution is both technically and economically viable for domestic use. Expected benefits and results. Optimal scenario. Under controlled conditions, chlorine residual and suspended solids are achieved, enable safe reuse for cleaning or irrigation and reducing domestic water consumption by over 50%. Realistic scenario with variable detergents, lots longer sedimentation time or higher coagulant dose may be needed. Critical scenario. In case of excessive solids or poor maintenance, turbidity may exceed 20 to 30 NTU or chlorine residuals may drop below safe levels. Conclusion. The development of project demonstrates that greywater treatment in homes is not only possible, but also highly effectiveness. When implemented using accessible technologies or prototype based on a multi-stage filtration system and high-pressure diaphragm pump achieve a 50% reduction in water waste, proving that small innovations can have a significant impact on the responsible use of resources.